As the demand for energy continued to increase over the last few decades, it became obvious that a clean, efficient source of fusion power was needed. The only known element capable of making that happen was helium-3. This is because the proton-to-neutron ratio of helium-3 is not balanced, 2 protons and 1 neutron to be exact, and so it has the tendency to take a neutron from the deuterium atom to create helium-4. But there is only one accessible place to obtain it: the Moon. This is the site of the world's first elevator into space, chosen for its proximity to the equator, where the Earth's rotation is the fastest, and the direction of the centripetal force, which keeps the cable taut, is perpendicular to the ground. The cable is made of carbon nanotubules. We are now inside the cable runner. Powered by electromagnetism, the cable runner accelerates away from the Earth at 1 g for the first 3,300 miles of the ride. This means that at the beginning of the ride, the astronauts feel as if they weigh twice as much as they actually do. But this number steadily decreases as they move farther from the Earth, because gravity is inverse squarely proportional to one's distance from the center of the body. After the first 3,300 miles, the power shuts off, and the astronauts freefall the rest of the way to the station, arriving at a snail pace. This ride would take the astronauts nearly 3.5 hours to complete. We are now at the geostationary orbiter, the largest man-made structure ever put into space, 38,000 miles from the surface of the Earth. From here, the shuttles to the Moon, nicknamed lunar bullets, can be launched using only a small amount of fuel, reducing the cost drastically. The lunar bullets travel through space for a few days and then touch down on the Moon, ready to transport the helium-3 back to the station, where it will then ride the elevator down to Earth. This is the moon base responsible for the collection and extraction of the helium-3. A giant conveyor belt scoops up dust and rock and moves it to the processing plant. This belt is slowly rotating in order to collect from a larger area. Inside the processing plant, the moon dust and rock is ground down to very small particles. This increases the surface area, exposing more of the elements, and makes it easier for the rock to let go of the gases trapped inside. These tiny particles are then sent into a sealed container, where it is superheated to thousands of degrees. This releases the gases and pressurizes the container. A valve is then opened, and the gases are forced out of the container by this pressure. These gases enter another container which does exactly the opposite of the first, cools the gases. Helium liquidizes at the lowest temperature of any gas. The temperature inside the container reaches nearly absolute zero, and all other elements turn to liquid, but the helium remains in its gaseous state. Once the container is drained, pure helium is all that remains, of which helium-3 is an isotope. A similar process is then executed with the helium. The more abundant helium-4 will eventually liquidize once it has been cooled down very far, but the helium-3, when at just the right temperature of about 7 degrees Fahrenheit above absolute zero, will remain a gas. The helium-4 is then drained, and the helium-3 moves into a shipping container. If we were to process the top 100 feet of 1,000 square miles of area on the Moon, it would be enough to power the United States for 100 years at the current consumption rate, diverting the energy shortage catastrophe for millennia to come.